Hi folks, welcome to section 2.7 where we're going to be meeting the derivatives of inverse functions. This is the final section in our unit about derivatives, and this is also the final set of new derivative formulas. After this section, we'll spend the rest of the semester investigating ways that we can use derivatives in some different real-world situations. So by the time we get to the end of this section, you'll be able to find derivatives of exponential functions. We'll review those. Find derivatives of log functions. Those are new. Find the derivatives of inverse trig functions. We'll have to review those a little bit too. And then use the relationship between a function and its inverse to do some derivatives of more general inverse functions. So in this video, we'll start with exponential and log derivatives, and then there'll be a second video about the inverse trig derivatives and a third video about general inverse function derivatives. So a little bit of review about exponential functions. We've known from way back in 2.3 that the derivative of e to the x was still e to the x. I'm claiming that in 2.5 we learned that if I have e to the kx, for example, if I had something like e to the 5x, then we learned in section 2.5 that the chain rule tells us that that would be, I would have to take the derivative of this exponent, so that would be 5 e to the 5x. I need to put my derivative here. Otherwise that looks like a really strange equation that's not even true. If I have something like b to the x instead of e to the x, this would be like if I had a function where I wanted to find the derivative of, say, 5 to the power x. Then the way we did that before was we did the natural log of the number part, and then we kept the 5 to the x. And we remember that that came from a funny way of rewriting 5 to the x as a power of e that had a natural log in it. So what if we wanted to do the derivative of something like this? 5 times 2 to the 3x. So to find the derivative, the 5 is just a constant, so we leave it in front. And then we're going to have to think about how we do 2 to the 3x. Well, just like e to the 5x here used a chain rule, that 2 to the 3x is going to use a chain rule. So maybe I come off to the side a little bit, and I say what the inside and the outside are. Inside, outside. Inside is going to be the exponent, just like it was for e to the 5x. So inside will be 3x. Outside, my f of u will be 2 to the u. So then I need to find their derivatives. U prime is 3. And f prime of u, this one uses the exponential rule, will be natural log of 2 times 2 to the u. And then to put all of that together, I'm supposed to multiply. 3 times natural log of 2 to the u. And so this part is what I'm going to put up here. I've got 3 times natural log of 2 and 2, but 2 to the u looks really funny right here because my equation had x's in it, not u's. So I'm going to replace that u, change it back to 3x. Alright, there we go. And we could go ahead and multiply this 5 and 3 together, and that would give us 15 natural log of 2 to the 3x. And this is as simplified as it gets right here. That arrow looks really confusing right now, so let me rearrange it. This went right here. Okay, so that was a little bit of review, but the reason we're reviewing it is because we're about to start working on log functions, and those are inverses of exponential functions, and so that will help us to see where the rules come from. If you look on your derivative formula sheet, there are 3 log rules. And I've repeated them right here. We've been using the one about natural log from the very beginning, as soon as we started meeting derivative formulas. But this one about log base b is new, and this one about natural log of absolute value x is new. The reason that we have 2 natural log versions comes from the fact that the domain of a natural log is only from 0 to infinity. So this is the graph, y equals natural log of x. So this is only good for x in the interval from 0 to infinity. Well, in certain cases, we'll want to be able to take natural logs of something that's not necessarily positive. And so the way we would do that is we would put absolute values around whatever we want to take natural logs of, and that's why it would be important that we know its derivative. However, the nice thing is that the derivative is exactly the same, whether you have absolute values or not. The only thing that is different is the domain of the function. So if I have absolute values, then x is allowed to be any number in between negative infinity and, not negative infinity and infinity, because x is not allowed to be 0. But it could be negative infinity to 0, union 0 to infinity. Any number except 0 would be okay then. Alright, so we want to do a little practice with these guys and talk a little bit about where on earth this formula came from, because I'm noticing I've got this natural log b thing going on again that looks kind of a lot like this thing, except it's a fraction. So what's up there? So to see how we came up with those formulas, we're basically using inverse functions and implicit differentiation. So I want to remind you that an inverse function means that you switch the role of x and y. So if I say y equals natural log of x, that is the same thing as saying that e to the power y equals x. Well, we could take the derivative of e to the y equals x. We could take the derivative of this. We would just have to do implicit derivatives. So we would take derivatives on both sides. So the derivative with respect to x of e to the y would be e to the y times a y prime or a dy dx. And the derivative with respect to x of x is just 1. So that's going to say, when I try to get y prime by itself, that y prime is 1 over e to the y. Well, now I'm going to use a little bit of information about what logs mean. 1 over e to the y, that would be the same thing as 1 over e to the natural log of x. And somewhere in your previous math career, I hope that you learned that e and natural log are opposite operations of each other. If I do e to the natural log of x, then all that ends up giving me is just x, because they are opposite operations, they undo each other. So it comes back to just x. Well, wait a minute. That's exactly what we got for the derivative of natural log x. It really didn't just fall from the sky. It came from implicit differentiation. So something similar happens with this log base bx and x equals b to the y. I'm not going to go through that one, but the idea is exactly the same, where you take implicit derivatives on both sides, and then you do some replacing and simplifying, and you will come up with the derivative formula for log base b of x. So let's just do some practice with these log derivatives. If I want to find the derivative of log base 3 of x, then the number that is playing the role of b in our formula, remember our formula was that f prime is 1 over log, not log, try that again, natural log of b times x. So in this case, that means 1 over natural log of 3 times x. And that's really all there is to this one. It doesn't have anything fancy. It's just a plain old log base 3x. So let's put a little bit more together. Let's do e to the 3x natural log of 2x. All right, so we're headed towards a test where you got to be able to tell which rule to use when. If I look at this whole problem right here, that whole problem is a multiplication. And if I split it between the e to the 3x and the natural log of 2x, I would be using my product rule, and I would have u is e to the 3x, and v is natural log of 2x. So that means that my derivatives are, derivative of u is going to be the derivative of the exponent first, so that's 3, and then I repeat the formula, e to the 3x. For v, this is really an inside and an outside again, but I want to start learning how to start thinking about shortcutting that a little bit. So the inside part is clearly the 2x. If I take the derivative of that 2x, I just get 2. So that part is going to be my u prime, or my inside prime. Well, then the outside part is natural log. And the derivative of natural log is normally 1 over, normally we would say u, because it would be a chain rule. But if I replace that, then I'm going to get 1 over 2x. And 2 multiplied by 1 up here gets me a 2 on top and a 2 on the bottom. So that simplifies to just 1 over x. So now I need to put all of those parts together to get a final derivative answer. It goes u prime v plus uv prime. And so that looks like 3e to the 3x times natural log of 2x. And then u is e to the 3x, and v prime is 1 over x. And there's not a lot I can do to simplify that, but you might be more used to seeing that last fraction written a little differently. We would more likely write this as e to the 3x over x. And so there's our answer. Now, a couple of things to keep in mind here. This was a product rule because in the big picture, this equation was a product. However, each individual part of that product, my u and my v, those required a chain rule to see an inside or an outside. So we really did both of those things here, and the key is in recognizing which one do you start with. The other thing I want to point out is that I shortcutted the chain rule a little bit here by saying that, well, this 2 is the derivative of my inside, and my outside is natural log, so its derivative is 1 over u. It is okay if you're feeling really confident and like you've done a lot of chain rules and you're good to go to make use of something like this. However, if you need to still write it all out, here's my inside, here's my outside, here's my inside derivative, here's my outside derivative, that is perfectly fine too. I just want to say if you feel comfortable taking the shortcut here, you're welcome to do that. All right, one more log function. This one, at the end of the day, this is a quotient. Yes, it's a quotient with a lot of parts, but the only thing I can do that will use the entire function is to think of it as a quotient. So if I'm going to think of it as if I'm going to think of it as a quotient, then I need a u and a v. So my u will be 7e to the 3x minus 3 to the x, and my v will be log base 5 of x. So then u prime is going to be 7 out in front. The derivative of e to the 3x is just 3e to the 3x. The derivative of 3 to the x will be natural log of 3 times 3 to the x. And then my derivative for v, my v prime over here, will be 1 over natural log, this time of 5, because that's the base of the log, and an x. Very important that we get these parentheses right so we know that the 5 is inside the natural log, but the x is not. So then my quotient rule for derivative says this is u prime v minus u v prime, all of that over v squared. So that's going to look like, let's see, u prime is 7. I'm going to go ahead and multiply that 7 and that 3 together. 7 times 3 gets me 21e to the 3x minus natural log of 3, 3 to the x. That's my u. V was log base 5 x. And then u was 7e to the 3x minus 3 to the x. And v prime was 1 over natural log of 5x. All of that stuff goes over v squared. So log base 5x, whole thing squared. And this is very much one of the ones that I would not ask you to simplify. You could leave this one just like it is and I would be perfectly happy. So that wraps up our section about exponential and log functions. In the next video, we'll move on and talk about inverse trig functions.